So we have 2 minutes past 3 and a good number of people in the room. So I suggest that we begin to start, and more people will trickle in. I'd like to welcome everyone to this distinguished lecture. It's our great pleasure to welcome Dirk Englund from MIT. Dirk actually visited Erlangen a few years ago and gave a colloquium in the physics department, but we're happy that he's, back. If I start his CV in a reverse chronological order, then I would say that he has just received a Humboldt Award to spend some time in Germany, particularly at our institute. So we were hoping that he would be sitting in our building and giving this talk. But I think it's planned that he will join us soon in 21 to have a research stay with us. And now to go back to maybe the beginning of his career, he studied physics, got his bachelor at Caltech. Then he had well, one has to say that he was born in Germany and then moved to the United States when he was a teenager, studied at Caltech, and then had a Fulbright fellowship at TU Eindhoven. Then he finished his master's in electrical engineering and got a PhD, both within a graduate program at Stanford. Then he went to Harvard to do a postdoc. And shortly after that, he became assistant professor at Columbia. Shortly after that, he went back to the Boston area, to Cambridge, and became a faculty at MIT, and then he became tenured, and right now he is an associate professor at MIT. He has won a number of prizes, including Presidential Early Career Award in Science and Engineering, Sloan Fellowship, and Adolf Lohm medal, and I also told you about the Humboldt Research Fellowship. Dirk has been working on a number of very exciting projects from his early time during his PhD with Jelena Vukovic at Stanford. And in particular, I would say he's very broadly interested, but kind of a red thread has been a lot of quantum nanophotonics in his work. And today he's going to tell us how to proceed, how to process exponentially growing quantities of data. Dirk, the floor is yours. If everyone please note that this will be recorded, this talk, so just for you to know, and make sure that your mics are off.
Great. Thank you so much for the introduction, and many thanks for the invitation. It's great to be back, even if only virtually for now. And I look forward to spending more time at the Max Planck with you and other great colleagues next year. So I wanted to, indeed, like Wahid said, I wanted to talk a bit about these nanophotonic devices that we are developing, and we're sort of entering a new stage at a point where they reach a complexity where we can do some things that are difficult to do otherwise in quantum computing and in machine learning. And just to sort of foreshadow the kinds of systems that I want to talk about, I've pasted two of them here. One is this, the ability now that we can place high quality artificial atoms, these are color centers in diamond, into photonic circuits. And here's an example that we just published a couple of months ago on 128 channels of diamond waveguides that have been implanted with various color centers, silicon vacancies and germanium vacancies, for example. And these behave very, very well in that their optical coherence is nearly as good as it can be, and they have good spin coherence properties as well. And then as far as the scale of the photonic side, that is also rapidly increasing, where nowadays it's possible to control hundreds of degrees of freedom with high precision analog with 10, 12, 15 bits of precision. And here's an example of one of our more recent circuits. This is a circuit with 500 degrees of freedom in the form of phase modulators in Mach-Zehnder interferometers. So you can start putting these things together and think about sort of applications in the areas that I mentioned. But before I go there, I just wanted to sort of set the stage a little bit of how fortunate really we are in today's technology. Here is a presentation from CBS News that Walter Cronkite gave, a big newscaster in the States, from 1967, and I want you to watch it.
This is where a man might spend most of his time in the home of the 21st century. This equipment here will allow him to carry on normal business activities without ever going to an office away from home. This console provides a summary of news relayed by satellite from all over the world. Now, to get a newspaper copy for permanent reference, I just turn this button. And out it comes.
There's your newspaper. Wow, pretty cool.
When I've finished catching up on the news, I might check the latest weather. This same screen can give me the latest report on the stocks I might own. Now, this is where a man might spend most.
And I want to stop it here. And this is a great video. I highly recommend it. You can find it on YouTube. That was what in 1967 was the vision of 2001. And we have far exceeded that vision, haven't we? And where he stopped there was on a weather report. Even the weather report, which we take for granted today, is a pretty remarkable thing. Here is one of the early computers, the ENIAC. This is from late 1940s, built at the UPenn, built for the purpose of weather prediction in part. And thank goodness that we have these amazing machines nowadays, because if you look outside, you can see here that Boston was hit by a blizzard last night. And thanks to these computers, everybody knew about it several days in advance. MIT is closed today, and I'm able to work from my office of 2001, the office of the future. And that I can talk to you this way is really quite remarkable. But at the same time, I think we modern humans tend to also be a bit cocky about where we are. I mean, those people back then, they weren't stupid, right? I mean, what do you think people will think of us 50 years in the future? So suppose that there's somebody giving a hologram presentation 50 years in the future, in maybe 2070, and they're looking back like we do here at these poor humans 50 years ago. And here is what they might have, the Homo sapiens of circa 2020. Here he is trying to figure out so desperately how high temperature superconductors work. He's got this material in his hand, or perhaps, in front of him, that works at high temperature. He knows that there's some sort of a weird correlated many-body quantum effect going on, but he can't compute it. Poor human Homo sapiens of 2020. And how do these molecules work? How does that molecule work? How do we predict or compute, how to combat that molecule of the great epidemic of 2020? And the Homo sapiens of 2020 didn't even know how to solve small optimization problems like maximum independent set or max cut problems on graphs of a few hundred vertices. Oh, the dark days of the 2020s, perhaps they will think. So the point is that it's really quite, I think it's just astounding to think about if progress does continue the way it has over the last decades, how much there is to do still, and how many discoveries there are to be made, and that makes me really happy to share this time with you all. This is a pretty exciting time in technology, and maybe we're seeing the glimpses of something new and remarkable right now. And one of those really, is this complexity that we're up against. There's so many things that we can't yet compute on, and one of them is this massive amount of data that we can now generate. And how do we compute on that? Because if we could do some remarkable things. And that's pretty clear from when you look at machine learning, at the complexity in machine learning in particular. So this here is a plot from the early days of AlexNet, when it was shown that machine learning tools, deep neural networks in particular, were quite good at some tasks like vision. And this here is the complexity of the networks that have been trained. Here is, this is the number of model parameters. This is the number of weights that you have connecting artificial neurons in these deep neural network schemes. And you can see an exponential rise. And the most powerful deep neural networks also have exponentially more weights that have to be trained. And that means exponentially more processing steps to train them. So training a modern day neural network consumes, supercomputer size resources, oftentimes for months running, okay? Can we continue that? Probably not. These supercomputers already consume megawatts of energy. So you have to think about doing things differently, okay? That's an opportunity for scientists and engineers to try to tackle those challenges. And one thing that goes in this direction is, I think, this other complexity frontier, and that's the frontier of quantum information. So we all know about the result announced in 2019 that Google showed a circuit that samples a certain mathematical distribution, a certain probability distribution, and it can sample that problem in a way that a classical computer would take exponentially long time to perform the same sampling operation. This is sampling a distribution produced by a circuit on a superconducting machine. And similarly, the similar kind of problem was reported just maybe a week or two ago by this group here of Zhenwei Pan and others that showed a sampling problem similar to the boson sampling problem proposed by Arkhipov and Aronson in 2011 that shows a computational, as far as we can tell so far, a quantum computational advantage in a similar kind of problem. Now the machines here are in a way pretty primitive. This here only uses 50 or so qubits. This here uses detectors on 100 optical channels, but nonetheless we see perhaps the beginning of something kind of profound where we are able to make new machines that are not like our conventional von Neumann digital computers that can do things that no other machine that we know of can do. And so it's sort of a renaissance in computing. So, pretty exciting time, I would say. And so what I want to talk here is so we've been fascinated by this, and we've been thinking about how we can apply some of these photonic circuits that I talked about earlier on to these problems of computation, of seeing if we can make tools to quote unquote program complexity. And I want to talk about a spectrum of applications here. On the one hand, use these optical circuits as a tool for controlling qubits in the atomic domain. This is in collaboration with researchers at MIT and Harvard, Lukin, Vuletic, and Greiner, who can trap atoms, cool them to ultra low temperatures of microkelvin, so 10,000 times colder than that superconducting device that I had on the previous page, and even nanokelvin temperatures, and then array them into registers. And then at that point, you want to be able to program them. You want to have an interface to apply gates. That requires new technology that we don't presently have, that essentially you can think of as a fast light projector, like a projector we have in a conference room, but one that operates at the wavelengths necessary for these atoms, and that can shutter pixels on and off at timescales commensurate with gates in these quantum memories, these atomic memories, and those gates can be as short as a few nanoseconds. Okay, so there's no projector that can do that at the moment, and that's one of the things I'll talk about here, about developing solutions for. But once again, here the optics is semi-classical. These are laser fields for control and readout. Another application, though, that's I think really exciting in our field of quantum information science is in quantum networks, where we use photons actually as information carriers to shuttle information between stationary long-lived qubits, and for example, atoms like these, like rubidium or so, or color centers, like I mentioned on the first page in diamond. Furthermore, if you can get, maybe you don't even need these atoms to carry the information. Maybe you use photons to do the heavy lifting. Then you need clever techniques to protect photons against loss. But if you make materials that allow us to apply gates between photons efficiently, then we know how to implement error correcting, including against loss, codes to ensure that quantum information continues to live on in photons, even if the photons are occasionally lost. And just as an example, I think some of the stuff that Professor Sundvector works on these strong nonlinearities in molecules is a really exciting way of mediating strong interactions between photons to do that. And finally, perhaps you don't need these nonlinearities, these inline nonlinearities between photons at all, and you can instead do nonlinearities by photodetection. This is something I won't talk about here, but I think I should put it there for completeness. This is on the far side of the spectrum where you just use nonlinearities in photodetection, and Milburn, Laflamme, and Knill in 2001 showed us that even with photodetection, it's possible in principle to do fault-tolerant quantum computing, although a lot of stuff has happened there in building better error-correcting codes, in particular using cluster states like the one indicated here. Okay, but across the spectrum, there's a need for photonics that should be co-designed between algorithms, photonic control, and the actual hardware. And so that's the part I want to sort of cover in this talk. And as acknowledgements, of course, I need to mention the fantastic people in my group, PhD students and postdocs who have made this possible, and I'll mention them as I go through. But also this wouldn't have been possible without amazing collaborators and funding agencies. So I want to start with that first problem of the present day complexity problem on machine learning. And to do this, first introduce our tool and show you how potentially that can help maybe solve some of the issues that we have in the field. And this is these programmable photonic integrated circuits that we recently published a review on that you can find here if you're interested. So machine learning, right, has many different sides to it: vision, games, control, speech, and language. But underlying it is a need for lots and lots of matrix processing. So here's a matrix processor that works on just 2 inputs and 2 outputs, very small, a 2x2 matrix. And this is something that's very familiar with everybody here for sure, a Mach-Zehnder interferometer. So you have an optical field entering on one arm, for example, and by programming the internal state of the Mach-Zehnder interferometer, we can make that field emerge at the other side in some relative amplitude distribution given by transmission and reflection of these 2 fields, and a relative phase amplitude. So we can represent that by a matrix, a 2x2 matrix. It has 2 degrees of freedom, perhaps with a global phase, 3 degrees of freedom. Reflectivity, relative phase, and if you want to keep track of it, global phase. But normally you don't have to, so it can be represented typically by 2 degrees of freedom. Okay, so now that you have this very simple 2x2 matrix, you can tile it into more complicated arrangements to create arbitrary programmable n-by-n matrices. And how to do that was actually already shown to us in this paper down here from 1994, Rex Dahlinger and others, who proposed this arrangement. What you do is you have, let's say you have 6 input modes connecting to 6 output modes, and you want to be able to implement any unitary transformation between them. They showed us how to program a set of Mach-Zehnder interferometers that are tiled in this triangular arrangement to accomplish that implementation. And how many degrees of freedom do you need? Well, the matrix is a unitary matrix of size n, has n times n minus 1 over 2 degrees of freedom. So for complex numbers, gives you of order n squared degrees of freedom that you have to program. So if you count up the number of degrees of freedom that I have in this arrangement, you'll find that this is in fact that number. Okay. Another way that you can do it is, you can arrange them in a different way. This is the same number of degrees of freedom, the same number of tiles if you counted it. But this is, as you can see, a bit more compact. So this is this Clemens paper from 2016. That's that's a implementation that we nowadays use because we want to make things a little bit more compact on our photonic circuits. And we represent one of these Mach-Zehnder interferometers by this kind of a waveguide implementation. What you see here is a silicon waveguide. So index is 3.5, surrounded by silicon dioxide, oxide, as we normally refer to it, on the outside here, with an index of about 1.5, 1.4. So you have an index confinement that keeps light in this waveguide. The dimension of the waveguide is roughly the wavelength divided by twice the refractive index, so that you have half of a wavelength in every dimension, that single mode waveguide. And so you come in here with an optical field. There's this thing here where these 2 things come together. Light can evanescently transfer from one waveguide to the other. We call that a directional coupler. And then so that implements your beam splitter. Then you go into 2 phase modulators here and another phase modulator on the outside. You'll notice that this thing actually has 3 degrees of freedom, although we said in principle we only need 2. And the reason why we have 3 is primarily for loss balancing. We were worried in making these circuits that the loss in the two arms of the Mach Zehnder should be the same. So we just put this dummy modulator here. You can see it's actually not connected to anything. The other one here is connected. This is connected to an electrical lead. Okay, and I'll tell you in a bit how these modulators actually work. But here you can see that as we apply voltage across this device, in this case, this is a thermo-optic modulator. So it runs current through this waveguide, where the waveguide itself is intrinsic silicon and the contacts are made of doped silicon. So you have low resistance, then a high resistance through the waveguide itself, and then again a low resistance contact. So that puts most of its power is dissipated when you apply a voltage, running a current through it, into the resistor. In fact, the power goes as V squared over R. And so if I'm plotting that power against the splitting ratio, you can see that you have you have a clear extinction here of the input field measuring the output intensity here. As I sweep across the phase applied by this modulator, I can get up to 50 dB of contrast. So 50 dB of contrast is pretty good. That means that you attenuate the light by 100,000 times from one to the other. So these devices work very, very well. They're if you're doing this in free space, it would be very difficult to anybody who's tried it. I have. It's difficult to get that kind of a modulation contrast in free space because mode matching becomes tricky.
Okay. Can I ask a question?
Yes, of course. Yeah.
So when you talk about that extinction contrast or efficiency,
yes,
does that include, let's say, device perfection issues like light scattering into your fiber anyhow? Because getting 100,000 is quite remarkable. Are you only talking about the on-off efficiency of the modulator, or are you talking about the actual signal that comes on the other side?
This is the actual signal that comes out the other side. We do take measures to try to reduce the any stray light passing through. For example, we have, on the input light, we spatially filter it, just like essentially we make a black box like that you would do on an optics table to avoid stray light that might come in from the input from reaching the output. Okay, but yeah, the devices themselves are pretty reliably this high contrast. Yep. But even that contrast actually isn't necessarily good enough, and there are imperfections. I'm showing you here one of the better ones. And in fact, actually, Vahid's question is a great segue to this slide. So here we actually went through and characterized hundreds of these modulators. And from that, got a probability distribution model of how well each of these Mach Zehnder interferometer works. And they're not all perfect. In fact, any sort of residual error in the operation of these interferometers would add up. If you didn't control it, they would add up maybe in quadrature. But fortunately, we can compensate that because these errors are coherent errors. You can take, if for example, there's a defect in this Mach Zehnder interferometer, you can take a subsequent Mach Zehnder interferometer or a set of them to compensate against it. And so that becomes an optimization problem where to do a unitary transformation from input to output, you have to optimize over, ideally over the whole set of interferometers. That actually in and of itself is not an easy thing to do, and we don't know if we do it optimally. We used a nonlinear optimization scheme here where we simulated thousands of circuits of this scale here and estimated the fidelity of certain operations. And in particular, one fidelity, just as a proxy that we considered, is a post-selected C0 gate. I don't want to get into how that works. It's just a bunch of settings of beam splitters. But it's like, sort of a representative mid-scale little circuit. And if you assume that the beam splitting ratios are sampled from the distribution that we measure experimentally, which has a mean of 50%, for example, splitting ratio on the beam splitters, but a standard deviation of 4%, then we get, and moreover, there is some loss in the thermal optic modulator. Also, that's not always the exact same. So that would also cause a infidelity in the overall transformation. Then if you didn't do anything, if you just try to sort of simple, stupid, program each of these Mach-Zehnders, then, for example, the fidelity of even this rather small circuit would only be of order 90, a few, low 90s in percent. That actually matches what people have seen experimentally in some of the early papers in these, in that particular C0 gate circuit. Now I realized, all right, this paper, for example, has that kind of fidelity. But if you use this circuit and program it like in this error correcting way, if then we show in this paper that you can increase the fidelity close to unity. So that's an important thing. If you used, like, one of the big challenges going into this project for us was, if we make these big circuits, how do we know that the errors won't add up in a way that makes it useless? Right? Like, the early computers had that problem. Analog computers still have that problem. You need some form of correcting errors so that they don't compound and make your computer useless when it gets to a certain scale. And here we think that at least these circuits for these linear optical transformations can be nearly perfect, even though internally they are imperfect. Okay, and I should point out there's similar work done by David Miller, a very nice paper here that has a similar result. Okay, so then that gives us confidence that maybe it's actually useful to build these things. So we built this circuit. We're not the only ones in this field. There's lots of great work from other groups as well, and we had a recent review paper that I mentioned already down here. So here, but let's take a look at the circuit that we built. This thing has 26 input modes, 26 output modes, 88 Mach-Zehnder interferometers. You'll say, hold on a minute, you should have 26 squared. The reason why that's not like that, 26 squared divided by 2, I should say, or 26 times 25 over 2. The reason why we don't have that many is because, you see, we couldn't accommodate all the wires. So we used a subset. So this actually does not do all unitary transformations. It does a subset of unitary transformations. It can do all unitary transformations, but only over the middle set of the 4 modes in the middle here. And over here, you're a bit more restricted. You can't do all possible unitary transformations. In a more recent chip that I didn't put in here, we have done the full unitary transformation, so we connect everything, but it requires a new technology for wire bonds. You see here, we had to apply about 200 wire bonds. This is very difficult to do. You have overlapping wire bonds. Anybody who does wire bonding will see this can become quickly a nightmare when you have wire bond on top of wire bond. In the new technology, we use bump bonding, which allows us to put electrical contacts across the entire area of the chip. That's what is more representative of modern day integrated circuits in bump bonding, but it required a new technology node to spool up. So this thing was a workhorse for us, and still something we use, and it's pretty great once you have it set up. It took a long time to get it working, but once you had it set up, it's a programmable optical circuit that you can use for many things. I put some of them down here, but I want to focus here on one in particular, the machine learning application, and see how we use the same kind of circuits in incorporating these quantum devices. So the point with the machine learning is as follows. So suppose that you have an input vector encoded in the amplitudes of input fields. Suppose you have in here 26 input modes, and each amplitude encodes the value of a number. Okay, and we can program that with about 10 bits of precision. I think maybe 12 bits of precision. We don't use the phase, although you will say, phase is another degree of freedom that we should make use of, but we don't in this example. So that's, so that's about 12 bits times 26 worth of information going in. And then by passing through the circuit, we apply a unitary matrix, and then it passes out the other side. Simply by flying through, this device applies a matrix transformation on the input, producing the output, u times x. So this actually is kind of useful in machine learning applications, because when you look under the hood of all these wonderful applications, one of the key bottlenecks in implementing them on conventional computers is the need for doing lots and lots of fairly low fidelity matrix vector multiplications. So you have an input. This might be an image, for example, to your neural network. And then what the deep neural network that underpins many of these demonstrations does is it transfers that information to a number of hidden layers. And you can see they're all connected in this case. And what you have to compute is how do the input values from this layer get transformed to the next layer. Okay, you can represent that thing by an n by n matrix, and then you have to multiply that n by n matrix by a 1 by n vector. Once you do that, you apply nonlinearity at these layers, and then you continue this. Okay, and the number of weights here is what we saw earlier in the plot. That's increasing to millions of parameters in these deep neural networks. So you can appreciate that you have to do lots and lots of matrix vector multiplications. So now when we consider how much energy that takes, so how much time it takes for a optical circuit to do this, well, you have to encode, you have to do of order n operations to encode n analog amplitudes. And then the rest of it happens on the fly. The computation happens as light passes through, so no more effort needed. Okay, so the computing of this matrix vector takes of order n operations on the optical device, whereas on the digital computer, you have to multiply. If you think about how many operations you have to perform to multiply an n by n matrix by a 1 by n vector, well, you have to use every single term in the matrix. So that's n squared terms. So basically, the number of operations scales as n squared. Moreover, another thing that's challenging for digital computers is that all of these weight values have to, in most implementations, be grabbed from memory. So that actually is time consuming and requires quite a lot of energy to get all that information. Whereas in the optical circuit, it's there, it's programmed into the device. Okay, so you see in principle, there might be a scaling advantage. If we make optical circuits that are big enough, that optics can actually provide some net benefit to this problem. And so we tried as a proof of principle out this scheme here in a collaboration with Professor Marin Solticic, who actually suggested for us to do this early on when we were talking about some of these things. He had a student who was looking at, who was taking a machine learning class, and we then realized, hey, we could actually implement this on our circuits. And this is a 4x1 input, 4x1 output, and we showed in principle that that this can be done with sufficient fidelity on this kind of a circuit. Once again, we were limited at that point in the full connectivity to just a subset of that matrix that I showed. But as a result of that work, some of our students started companies, Light Matter and Lightelligence. And here is a Light Matter that's a company that I'm involved in. And what you see here is this company was started in 2017, and just earlier this year in August at a conference for integrated circuits, hot chips, NVIDIA and so on present there. They demonstrated their prototype, and so what this is similar to what I showed you earlier, but much bigger. This is a device that can do 64 by 64 transformations. It has sufficient bandwidth to compute tens of channels simultaneously, tens of spectral channels simultaneously, in a bandwidth of 20 gigahertz. The latency is very, very short because it's only given by how long light takes to transfer across the chip. That's sub-nanoseconds. And if you calculate how much energy you consume, well, first, let's see, if you calculate how many multiply accumulates, which is standard unit of measure of a unit of compute in a deep neural network, that thing performs its the equivalent of doing a 64 by 64 matrix multiplied by a vector every nanosecond, repeated over 10 input vectors, because you have sufficient bandwidth to do that. And from this calculation, you see that you get about 10 to the 14 multiply accumulates per second, which is similar to the number of operations that a modern day GPU, graphical processing unit, can do. Like a modern NVIDIA system is of the order of hundreds of, of the order, like the most powerful devices are like 100 teraflop per second. So it's similar in that regard, although not quite as programmable, okay, to be sure. But on the plus side, it has only tens of femtojoules of energy consumption per Mac, which is substantially lower than if you did this in circuits. Okay, so this is just a prototype, a hint of what can be possible, after several years, just a couple of years of development, a hint of what can be possible in lowering the latency and power consumption of deep neural network computers by this method. So we will see. I serve as a scientific advisor with the company. It's exciting times for sure, and you'll see in 2021 how this develops. So keep watching the field. I think it's going to be exciting. Oh, by the way, you can see the presentation of this company online, but they actually had to develop some new technology. They no longer use thermal phase shifters here. They use nanoscale MEMS micro mechanical devices as phase shifters. All right, so what I've shown here can be classified as what's called a weight stationary deep neural network implementation. Weight stationary because the weights are encoded and are encoded and fixed on the processor. The information flies through. There's also a weight stationary implementation using, electronic circuits. And there, of course, you'd say, hey, why don't you just make a resistor network? And people do that. We think that the optical scheme has higher fidelity because of what I told you earlier, that in the optical case, because errors are coherent, if there's a coherent error, you can cancel it. And moreover, you have far greater bandwidth of operation. We have, tens of gigahertz of operation bandwidth in the optical scheme. So there's an inherent advantage there to the optical implementation of these weight stationary schemes compared to electronic versions. The other thing I want to talk about briefly is what's called an output stationary implementation. The idea here is that the output stays put, okay, and you stream the input data as well as the weights in real time. There's also an analog for this in the electrical domain, but we have a similar argument for why optical scheme is better. And one thing in particular that I want to point out here. So in this paper from last year, we proposed this output stationary implementation of deep neural networks, where you use time multiplexing of data of both weights and the neural values. And then you still have to multiply these two, right? In the circuit, that happens just optically, the Mach Zehnder, the circuit just, does the multiplication as light flies through. But suppose you have two optical signals that carry the weight information and the neuron information. How do you multiply them without blowing your energy budget? So it turns out it's super easy. And I think this was just like so cool that this works. There is an extremely strong nonlinearity in optics, and that's photodetection. And it works at the quantum level, and it's quantum noise limited at optical frequencies. And so the way that works, this is everybody will immediately see how this works, basically, or anybody in optical communications, at least. So you take a homodyne receiver. You have two input pulses that have amplitudes X and Y. These pulses are combined on a 50-50 beam splitter, producing amplitudes X plus Y over √2 and X minus Y over √2. When you then do photodetection, that applies the absolute value squared operator, and you take the difference in current, and that gives you, okay, here's the current from one, current from the other, take the difference current, that gives you automatically the product of the values of X and Y. So then you can repeat that pulse after pulse for values of amplitude X and Y, Okay, and a photodetector does something else that's kind of cool. It, given a finite bandwidth, integrates, right? If you create some photocurrent, put it on a capacitor, and then the next pulse comes in, produces photocurrent also, it gets added to the capacitor. So you add charge on the capacitor, and what that does is performs a dot product between two vectors, x and y, okay? And it can do this ultra fast. It can do this with every pulse being just, a fraction of a picosecond long, because the photocurrent accumulation is ultra fast. What is typically slow on photodetectors is the readout. Okay, but you only have to read out after you've done, a fairly long vector. So for example, if you have 1,000 pulses, each 1 picosecond long, then after 1 nanosecond, you will have done a 1,000 by 1,000 dot product between two vectors, and then you read it out at a gigahertz readout rate. It's really quite remarkable that just replacing the local oscillator on a homodyne receiver with an amplitude, a modulated amplitude, gives you a vector-vector product. And it has very low energy consumption, and so then for the problem that we want to do here, let's take a input value and you distribute it across a number of receivers, and you stream in real time the weight values that every neuron needs to know as far as how to weight that input value. Okay, so you need like this 2D array of light being beamed into these homodyne receivers, and then that gives you your matrix vector product. You then feed that in the electrical domain into a nonlinear function, which is easy to do in the electrical domain, and then you repeat the circle. You go back into the optical domain and repeat it. So we tested the scheme out, theoretically at least, by modeling based on best estimates that we could derive for components, how well that kind of a system would work. We're now building it, but let me show you the simulation first. So here is an estimate of the energy consumption per multiply accumulate that you would have to expend on this in a modern day conventional implementation in digital electronics. And here's the number of neurons per layer. So plotted then here is, if you consider like a small neural network, then the optical scheme might be for conventional modulated technology and photodetector technology up here. So you might expend about 10 to the 13 joules per multiply accumulate, which is about on par with a digital modern day implementation. But as the problem becomes bigger, we saw earlier, right, the energy consumption for the optical scheme drops by a factor of n compared to the digital electronic scheme. And so we gain in the energy consumption per equivalent multiply accumulate. So here's current modulator technology. We estimate here that, for 1,000, for layers that are 1,000 by 1,000 that require the computation of 1,000 by 1,000 matrix, you would need about a femtojoule per multiply accumulate. But if you use sort of advanced photonics technology that we derived from research papers rather than something that I can put on the device now in the factories that we work with, then you can get a line like this. This is about a femtojoule per neuron. And what these plots here are representing is the energy consumption per multiply accumulate for a deep neural network implementation that is as good in its error performance on the MNIST digit classification task as the digital electronic computer. Okay, this is the equivalent performance in terms of the performance of the deep neural network, but now implemented on an optical device. So you see here that at some point, actually, remarkably, this device has an energy consumption that if you implemented it with a digital sort of conventional computer would require that computer to operate below the Landauer limit. What I mean by that is, we know that the energy consumption per gate operation is of order kBT, which is 1/40th of an electron volt. To multiply two 10-bit numbers requires of order 10 squared operations on a digital computer, accounting for additional overhead in multiplication of on a digital computer for registers to move and so on, it's about 1,000-bit operations that are required on a digital computer to multiply two 10-bit numbers. So then the Landau limit is 1,000 times kBt, which comes out to about 3 times 10 to the minus 18. Okay, that's that limit. So you see that it's possible for a device that uses optics as part of its compute to dip below the energy consumption of what would theoretically be possible on a modern day conventional computer. So why is that possible? Because here we use a combination of optics compute, and which is reversible, and the electronic compute, which is irreversible. Okay, so the optics computation consumes no power. It's a reversible computation. Okay. So motivated by this, we actually started to build these devices. And here's a snapshot. This is not yet published. Here's a snapshot of a transmitter that actually is intended to beam those pulses out. And we have a reciprocal side for the receivers. And that experiment is ongoing. We'll see how we get. I don't think we're going to beat the Landau limit equivalent right away, but we want to get the scaling behavior and understand if our calculations were on track. Okay, so also you shouldn't work in isolation. The electronics field is moving quickly also. And so we started collaborating a couple of years ago with some honest, leading people in the electronics community on machine learning accelerators. And in particular, these are Vivian Z and Joel Emmer, who are both faculty at MIT, who work with NVIDIA and so on developing their machine learning hardware. And we use the same simulation tools that are used there to model traffic, data flows and so on, memory access and all that. And that is ongoing work. We have an initial paper here that studies some of these benchmarking estimates in pretty great detail. Without going into the detail here, what I can say is that it seems clear that just the communication part itself doesn't give you enough of a gain for optics to have a big impact. But these, doing some of the computation in the optics seems to give us a possibly very large advantage. Okay, so something we're working on at the moment. And that, once again, here's that plot. That becomes more pressing as these neural networks scale. To continue the trend in neural networks, we have to do something different on the compute side. And perhaps this, we'll see, but perhaps this is a way to lower the energy consumption and the latency by a couple of orders of magnitude. We don't know yet, we'll see. Okay, now I want to move to the next topic. I'm going to sort of check my time here also. Okay. Now I want to move to the next topic. I'm going to speed up here a little bit on actually outfitting these kinds of circuits with memories. So I showed you these photonic integrated circuits. They're good at processing light. How do we combine that with quantum, single photon sources, single photon detectors, ideally also quantum memories? And in particular, I'm going to tell you briefly about how we integrate into these kinds of circuits color center quantum memories and what kind of applications that might enable. And this is done in this collaboration here, the Quantum Moonshot. So we want to add the special thing to it, something that has the ability to hold qubits for a long time, better than light alone, perhaps. And so we've been working with collaborators for more than a decade now on making high quality diamond devices. Early fabricating diamond films out of bulk diamond. We would take a bulk diamond and polish it down, from 500 microns down to 5 microns, and finally etch it all the way to a few hundred nanometers. And you see the result here. This is fantastic, for diamond suppliers, because we burn 99.9% of the diamond. So they're happy about it. But for us, it becomes very expensive. And it turns out the performance wasn't that great. The yield was bad. So we developed other methods that are shown here, and we can now reliably produce photonic crystal devices. In diamond, what you see this here is a photonic crystal. This is scanning electron microscope. The holes are air holes that produce a distributed Bragg reflector that resonates light around a site where a color center can be implanted. So we use different kinds of color centers. Initially, we did a lot of work with nitrogen Bigsby centers, and we continue to because they're amazing in many ways. But there's a number of other kids on the block now that are more stable optically. And one that we're very excited about these days is down here, the tin vacancy in diamond. You can take a look at this paper. That's a collaboration with Meta Ataturk's group or other references in that field. These are very stable optically, even if they're close to surfaces, and they seem to have very good spin properties as well. Moreover, it's possible to implant these color centers into diamond using a focused ion beam. You implant, you anneal, and you have a cavity QED system that is pretty good. Maybe not as good in optics as what Wahid works on, but they also have good spin properties. So maybe they complement one another. So then we learned how to make these so reliably that we can now make circuits that have 128 channels on them, where each single channel of them, here's one circuit. This is just taking snapshots. And this is no cherry picking. Here's 128 channels outfitted with 128 waveguides with 128 high quality color centers inside them. How good is the quality? You can see here. This is the scanning. This is a photoluminescence excitation spectrum. And it shows here the line width of each of these emitters is near 100 megahertz, which is very close to the intrinsic radiative time lifetime limited line width of 95 megahertz. So these are very close to how good of an emitter you could possibly have. And you can close the gap by putting them into cavities. Moreover, you can tune them electrostatically by straining individual waveguides. So all of these can be tuned to be in a common spectral channel. And once again, this is no cherry picking. This is showing one channel after the other. They work reliably. So now we have sort of a toolkit here. We have spins coupled to photons. We have, I didn't show that, but there's some references here too. We have photonic circuits. I didn't talk about this, but we have also developed with collaborators CMOS control circuits using TSMC foundry, like the same foundry that makes computer chips in your phones. We use that to do spin control, so that can be scaled. And then something I didn't talk about here, but it's also sort of something that we want to onboard in this toolkit is photon-photon nonlinearities. So where the outlook on this then goes is building quantum repeaters and separate work that was actually led by Professor Misha Lukin at Harvard. It's been possible to use these kinds of spin-photon interfaces to demonstrate a quantum advantage in communication. That's a really big deal, I think. Shows for the first time that with a quantum memory, you can perform quantum secure communication over longer reach than you could without. There's a utility, an advantage to using quantum memory. So that's that, and it basically forms the basis of where we go forward in deploying these multiplex quantum memories now in a test bed that my group together with Lincoln Laboratory set up in the Boston area. At the same time, we're interested in scaling these things up for quantum computing, and we're sort of building out this blueprint model that you can see here on an error-corrected, perhaps ultimately fault-tolerant platform. So this actually, we actually looked at how to implement fault-tolerant error-correcting codes based on Rosendorf lattices. It's kind of interesting and very happy to talk about it separately. So this is, I think, an exciting point for these kinds of photonic circuits to serve as, intermediates to relay quantum information between different kinds of quantum devices, the quantum Internet of Things that would consist of different sensors, different quantum computers, being able to pass information with no loss in fidelity in that information, that is at the quantum level. And that has lots of exciting applications. But that requires good interfaces. So I think another really cool area that we're working on a little bit is on building interfaces between superconductors. Like in this collaboration with Professor Will Oliver, we're looking at how do we make efficient interfaces between superconducting, quantum computing, and optical devices. Okay, to onboard these. But I want to return to what I set out with on machine learning. Suppose that we go back to that optical circuit that I showed you. Okay, like I can do that linear transformation, input light, we had the nonlinearities, and then we go and pass that on. But suppose that rather than having classical nonlinearities like photodetector converting optics into electrical current, we had some sort of quantum nonlinearities, right? Like these nonlinear devices that people at Max Planck Institute are developing, or these single artificial atoms in cavities. These are examples of nonlinear devices that would perhaps be used for this. And then you can say, hey, so you have this machine learning tool, but now it can process on quantum data. What can you do with it? Suppose that we use just like naively the same architecture, like a number of photons coming in. Now these are not attenuated laser fields. These are just, suppose that they're Fock states, like single photon states, for example. Can we do something useful? This actually requires kind of a complicated way of programming or compiling quantum algorithms on the circuit. And we did quite a lot of that. But then we said, hold on a minute. Why are we beating our head against the wall to make these compilers for what should be a machine that learns? This is a quantum machine that learns, but it still can we use backpropagation? Can we use methods like we normally use in machine learning to train this machine, this quantum machine, to do something useful? And it turns out you can. I can't say about the efficiency yet. We don't have, I think, in all of these things, efficient algorithms, but I'll show you one example. So here's a couple of different things that are published here. One thing that we wanted to see is, hey, can this device learn to correct a optical logical qubit? So you take an optical logical qubit encoded on 2 modes with Fock states 4 and 1. Okay, so this is logical 0, logical 1 is this. And you say, okay, that optical logical state has some loss in transmission. Can I train this black box? Okay, can I train the unitary in here to correct that circuit? I will, to help it out, I'll give it a couple of single photon input states as instead photons as well. Can it, given these ingredients, can it figure out how to repair that logical qubit? And it turns out they can. So we strung many of these behind one another. This is all theory. And after giving it like 30 to 40 layers of depth, this was able to get the output state error basically down to 0. So doing this experimentally would be really, really hard, up to 40 layers. But I don't know what the best compiler actually is. It's well possible that you could do this in 10 layers, but our optimization didn't find it. I think it's actually likely that you can do substantially better than this. But we don't yet know how to best program these quantum machine learning devices. Backpropagation doesn't apply in the same way that we have it in the classical case. So there's an interesting question here. Can you train black box quantum computers to solve their own error correction? Just like when you have a biological brain, it learns to configure itself for the task. Can you apply similar things to a quantum computer? So that's an open question. I'm really excited about it and look forward to talking to people about it, perhaps this afternoon. Last thing, these circuits are also quite useful for solving one other thing I wanted to mention, and this is in controlling some of the best qubits that we know about presently, and these are qubits in ultra-cold atoms. This is in collaboration, as I mentioned earlier, with these faculty members between MIT and Harvard. And the bunch of us also started this company, but on the university side, you see from the university groups here, you see this image. These are photographs of individual cold atoms. These are rubidium atoms that give off fluorescence. And these are the registers of this kind of a quantum computer. Now, amazing amount of work by these groups, like the biggest CAT states ever produced, for example, has been done just using global gates, applying laser pulses to an array of atoms simultaneously. We don't yet have the technology to apply individual gates, but you see these kinds of circuits that we're developing, they might, if we get it to work at the right wavelength, allow us to do that. And so if we can apply like individual red laser pulses. We can do gates on these. We can do 2-qubit gates by Rydberg interactions. What that means, you take the electron and put it out in a very high end state to sort of like you blow up the atom so that two atoms at a distance of 10 microns still have a strong dipolar interactions. And this is how you can apply logic gates. And so a big topic in the group that we're really excited about is building the optics that then projects the laser fields into the cold atom chamber to allow us to program the complexity in that machine that now has hundreds of qubits. It's at a point where you cannot predict the output of these experiments anymore. So this is, again, I feel like in a way we're sort of sitting at a computer terminal, we're running code and projecting it on a device that we can't predict. So we're kind of like programming complexities. We don't yet know if it's useful. We have to kind of just try it out by measurement, see if it was useful. But it's a really exciting time for discovering new stuff. And with this, I come to a summary. So I've shown you some of the hard work efforts going on and some of the applications. And along the way, I just want to mention that there's a lot of exciting opportunities also for motivated people to start companies. And quite a lot of this work is now actually transitioning into startups. And we'll see. It looks pretty promising so far. I think time will tell if these new technologies will lead to something that's truly impactful, that people will look back on in 50 years and say, hey, okay, there was something these people figured out that led to a new revolution. I'm sure somewhere it's going to happen, whether it's some of this work or probably other people's work, but things will certainly not stay the same. So once again, also acknowledgements to people who made this possible, and thanks a lot to you for your attention.
Well, thank you very much, Dirk, for this very exciting and clearly forward-looking talk. I'm sure there are questions. I haven't seen anyone writing questions in the chat line, but people can shoot. I see that Florian has a question, so Florian, just grab the microphone and.
Okay, hello. So thank you very much. You mentioned optical nonlinearities, but more in passing. So I guess that's because it's a little bit difficult now. If you want to implement them on the chip for any of these, what would be your best bet? What kind of nonlinearity would you use? Something atomic-based, spin-based, or just lithium niobate? Or what would you aim?
We will have to talk in more detail later. This is a long answer, but so let's see. I think so. Atomic systems with 3 levels, 2 ground states, already give us the nonlinearity that we need, because you can only, because you can mediate 2 photons interacting sequentially. The first photon comes in, it can flip the atom from one ground state to the other, and then based on the ground state of that atom, the next photon will either pass or it doesn't. So that's a nonlinearity that basically derives from some early work. Maybe we can attribute it to Dwan and Kimball. I think it's a 2003 PRL that proposed that early on. So that works, and these silicon vacancy centers are actually very promising for that application. In fact, that work led by that was led by Michael Lucan's group, that it did that. It was able to mediate a gate in a heralded way between 2 non-sequential photons. So that's already possible, but it would be nice if we could get away from having to do it sequentially. You could do it simultaneously and perhaps faster. And there's a long history of trying to do that with high efficiency. We tried that for a long time, and it turns out if you try to do it with a 2-level system, I think you run into some trade-off between fidelity and probability of the interaction working out. but if you couple the two-level system to something else, like a time-dependent dielectric medium, then it works out. Here's something that's related to that. In this paper here, we show this catch and release scheme. So you take a cavity, take the first photon, comes in, the cavity has low Q, and then you switch the cavity to high Q state in a way that captures this optical pulse perfectly. You can do that with 100% efficiency and fidelity. And then you hold it there for long enough to mediate an interaction. If you take if that pulse is excited by two photons, you get an overall nonlinear phase shift when you split them back out. So we've shown that this works for Chi2 material, but it also works, it's not published, for two-level systems. We're talking about that a bit with Wahid, and hopefully again this afternoon. That's one way that at least I know about, that it can work with a two-level system only. Okay. We have a time-dependent dielectric medium. This here, actually, since you mentioned lithium niobate, this thing here, this paper and this paper, they consider a Chi2 material, and they actually show that this high fidelity, high probability could be achieved using catch and release. With numbers that are hard, we don't have them yet, but they're not crazy hard. To give you a number, Q of 100 million, and a mode volume of lambda cubed. People are currently at a Q of about 5 to 10 million with that kind of mode volume. So it's like an order of magnitude hard. It's not like crazy hard. So I actually, if you just project out trends, I'm sure that the community is going to start hitting those limits. I think it looks actually pretty promising, I would say.
Okay, good, great, thank you.
So Stefan Götzinger has a question. Stefan, Dirk, if you could give kind of shorter answers and let people come back to you afterwards.
Yeah.
So I'm not sure if you partially answered the question already. You mentioned twice in your talk, and we see this on that slide, that you say there's this photon-photon nonlinearity even at room temperature. But this still involves a matter qubit, I guess. Can you expand on this briefly, what this means?
Yeah, so actually in this paper here, this is just using the bulk nonlinearity of lithium niobate.
Okay. That's sufficient in the cavity.
It's sufficient, yeah. The way it works is you capture an optical pulse. If it's excited with two photons, it can undergo second harmonic generation and back again. Mm-hmm. And if it has a single pulse can't undergo second harmonic generation. So it turns out that way you can show that there's exactly a pi nonlinear phase shift that you can acquire. But it does require high Q at two frequencies, I
see. Okay, thanks. Interesting.
Dirk, if I understood everything, the first part of your talk, or the chunk of it with your integrated circuits, was essentially kind of optical computing combined with neural networks. So how much of that has become possible recently because of which breakthrough? Hello?
People had the idea of doing programmable circuits like this for a long time, but achieving the device fidelity and in particular phase stability wasn't possible until really quite recently. Now that we have foundry processes available for some of these things, or in this case, we have, this is for the national laboratory, we can have very sophisticated fabrication. So that's one thing that had to come about. I would say that opportunity has only existed for maybe 10 years on the photonic device side. The other thing with machine learning, of course, is like machine learning has been known for, those ideas have been around for decades as well, but it required sufficient data and the ability to compute on lots of data to actually show that they can do something really useful. And so that's the second thing, and that only came about also in the early 2010s, right? Which with the ImageNet competition, for example. It's less than 10 years old, that realization. So, so it's a pretty new thing. People had actually proposed also doing like machine optics for machine learning, also quite a long time ago, but they didn't know that machine learning was useful 30 years, 40 years ago, and they didn't have the tools to implement it. But some of those ideas have actually been around in principle for a long time. Yeah.
So that means I don't know the literature very well, but that I gather from your answer that simpler circuits, which didn't need as efficient of modulators and components as you have now, had been demonstrated 20 years ago, or were people actually kind of going at it?
Yeah, so for this to work, first of all, you have to show that machine learning tasks, processors are useful. But suppose that they had been able, suppose we had known that for a longer time. Could you have done it with the hardware that they had 30 years ago? And the answer is probably not. And the reason is that you have to make these transformations be very high fidelity. When you implement, and at sufficient size. So you have to have matrices that are sufficiently large to derive a net benefit, because otherwise you just pay you pay a lot of overhead first off to go from electronic to optical domain. Yeah, so the hardware really isn't a necessary thing. You need to have, the matrix that you apply needs to be within 99% or so of the matrix that you need to apply. Otherwise, your neural network performance will not be as good as if you performed it on a digital computer. And then it's all about performance, right? So you're not willing to say, I'll take half the power consumption for half the performance. Performance comes first. So you have to match that performance. Yeah. That wasn't possible with earlier equipment, I would say.
Interesting. I mean, as a last comment, I guess it's non-trivial because 20, 30 years ago, computers were not as good as they are today. So at some point, you would have thought that maybe there was a window of opportunity for the optical technology to actually take over, but never did.
No, actually, there was. In fact, there were in the 1990s products that did Fourier transforms optically for signal processing. It's just that, fast Fourier transform combined with cheap, abundant CPUs made it cheaper to do that, even though maybe the performance latency wasn't quite as good as if you did it optically. But there were companies selling these optical Fourier transform instruments in the 1990s.
Okay.
So, but now we can do much more sophisticated things. I mean, and I should mention there's other companies that are pursuing the same direction. It's possible now to just have a lot more programmability on the transformations that you want to do. Yeah. I think maybe the other piece of urgency is that Moore's law scaling really has tapered out. Yeah. So we have to think again anew. This is sort of the renaissance of computing. People are thinking about new ways of computing again. So it's a great time for physicists to be part of the conversation again.
Yeah, yeah. So we have one little question from the audience, whether when you expect in general quantum supremacy to take over.
I think it's a very special purpose, so let's say I think I like to think of it as the advantage, so this quantum advantage, and there's different ways of looking at it. There might be an algorithmic advantage, maybe a polynomial speedup or something. I think the only exponential speedup algorithm that we know exists is probably still the Shor algorithm for factoring, but there's other schemes where we simply don't yet know. So how long will it take for like a quantum advantage? So arguably quantum computational advantage has been shown in these examples, but let's say a practical one, something that people care about. And I kind of think of it as a market-based driven advantage. That is, somebody wants to have some computation done, and whether Whether it's done on a quantum computer or not, they don't care. They just want to have the computation done at the fastest speed for the lowest cost. And so that kind of quantum advantage, when it's like truly market impactful, I don't know when it will come. We don't know. It could be 5 years. We don't know. Like there's indications that for some problems, like I'll give you an example. Doing the maximum independent set problem, which is a particular NP complete problem on a graph, is impossible for certain instances of graphs that are of size 300 or 400 vertices. Fairly small graph, you can't solve certain problems on it. It's not known how to do it. Classical computers cannot do it. And those are problems that actually are of practical interest for things, for routing signals, for example. That's an example. So they are practical interest problems that can't be done with today's computers that might be done with quantum computers in the next 5 years or so, but we don't yet know.
Okay, I take one last question from Fabian Wolfert. Do you want to ask your question yourself, Fabian? I'm not sure if I understand 100% your question.
Well, the question is about how the performance is in comparison to standard neural networks. So the time it takes, how much faster are they?
Oh, that's a great question. Yeah. They could win on latency because the matrix vector multiplication happens like instantaneously. They will not win on everything, but latency might be one. So the speed at which they can execute a computation is one where they would have an advantage. So that might be an early place where they, people might actually want to use them in practice. In terms of, so that's latency. And in terms of energy consumption, that is sort of the main argument in favor of them. So probably, so I think in 2021, you watch the space, there should be examples of, devices that are out in customer hands who will start benchmarking them, and they should be able to derive an energy benefit on some computation tasks. It has a lot to do with the problem. It has a lot to do with how you can batch it, because like these devices still require batch processing of data. So the exact problem type is very important, but there will be, I think, instances where you can derive an advantage. And finally, the one last comment is, I would say, on the performance. The accuracy, you can't compromise on it. So I think you have to develop optical circuits that are sufficiently good, or whatever analog thing you do, that are sufficiently good so that it's as good as if you did it with, a digital computer, even if that digital computer like consumed 10 times more power. Okay, so you cannot compromise there. And we think that's possible, but again, you have to watch the space.
Great. On that note, I thank you on everyone's behalf, Dirk, for a great talk and lots of questions and discussions. And we look forward to seeing you in person soon in Erlangen.
Ja, danke, gleichfalls.
Ja.